So I want to give a very high-level summary of a new coupling infrastructure that we are targeting for CSM called the Community Mediator for Earth Prediction Systems, or CMEPS. And I want to just go through several areas. Rocky already mentioned Neopsy yesterday, so I'm just going to give a few extra points about it. Then I'll go into summarizing what CMEPS really is, how we are collaborating with the NOAA Unified Forecast System right now to create a mediator that is used by two very, very different modeling approaches, but that have some shared components. What is its current status? And as part of our generation of CMEPS, we've also created a new set of data models that are used for turning off and on feedbacks between the different modeling components. And in the spirit of having the name CMEPS, we've called them CDEPs, or the Community Data Models for Earth Prediction Systems. So just in terms of ESFF Neopsy, I think that Rocky gave an excellent presentation yesterday, summarizing a lot of this, and I just want to basically add a few points here. So basically, ESFF is the de facto coupling infrastructure for the Navy, NOAA, and NASA. And the key point is that CSM is now adopting it as its coupling infrastructure for the next version of CSM, which is going to be CSM3, and we're hoping to actually bring it in as the default coupling infrastructure for what we call CSM23, which is the next development version of CSM that's going to be available for the community. As Rocky mentioned yesterday, Neopsy is a new interface layer that is provided with ESFF. So when you check out ESFF, you get Neopsy with it. And what it does is that it provides both building blocks and conventions for using ESFF to create coupled model systems and leverage the tremendous power of the ESFF framework, but with standardized conventions and object-oriented building blocks. So what Neopsy does is that it actually simplifies the technical interoperability of model components and targets the ability to share these model components across different coupled model systems. And that is, I think, a very powerful thing that without Neopsy would not have been as easy to do in the past. So what is CMEPS? So basically, our current approach for the community or system model, or CSM, is that it is a hub and spoke infrastructure, which means that all components that couple into CSM don't communicate directly with each other. There are no connectors directly coupling in the atmosphere to the land. So what they do is that they exchange all information with a central hub, and that hub is responsible for mapping source fields to the destination component or components with different mappings, and also merging a collection of source fields to the target destination component, where the merging can be done in different ways. And another key assumption and capability of the coupling infrastructure is that because the hub is ignorant of what is on the other side, the components have the ability to be able to have their prognostic components be swapped for what we call data components to selectively turn off feedbacks in the system. And that ability to turn off feedbacks in the system is what we refer to as hierarchical model development, where you can have particularly all data forcing of a prognostic component to do the first set of parametrization developments, and then you selectively start adding in prognostic components piece by piece until you have a fully coupled system. And as everybody that's worked with a fully coupled system knows, that when you do development with prescribed forcing and you suddenly turn on feedbacks, you get very, very unexpected results. And as Rocky mentioned yesterday, what we have to be able to communicate from these components with each other via this hub is what's called a CAP. And the CAP is really just a translation layer. It's a translation layer from the model data structures into the framework data structures and vice versa. So one key, I think, in my view, drawback of Coupler 7, and one of them, is that there really is no clear separation in the infrastructure between the driver, the hub, and the connectors. They're really all bundled together in effect in one driver code. And so it's very hard to say, well, we're going to share the coupler with other components, because you then have to share the driver as well. And the driver is set up with the workflow. And so there is, from that point of view, lack of modularity in terms of being able to have true interoperability of this coupling infrastructure with a whole other set of modeling components. So in adopting ESFF Neopsy, the hub, or in ESFF lingo, the mediator, is really just another component. And that is a real paradigm shift. This mediator can be shared with other components. As I'll talk later, the connectors are auto-generated for you, so they're not part of the driver infrastructure. And having this idea that a mediator is really another component on the same level as all of the other prognostic or data components is very powerful. So where the model-specific capability comes in, or restriction comes in, is that the drivers are model-specific, but the hub is not. So what happens when we put the mediator now in terms of the CSM components is that you can now still have the ability to have these data models be swapped for prognostic components. But now you have a whole set of components, which I've circled in black, that we are now sharing with NOAA. And these are the new size 6 CS model, MOM6, which is our new ocean component that is going into CSM, a new version of WaveWatch that has been created at NOAA, and that we are now able to easily bring into the system because of ESFF. And what I've circled in yellow is that even though we're not sharing it, there is a completely new atmosphere component that NOAA is using called the UFS atmosphere, which is based on the cube sphere finite volume that GFDL has created. And that can be easily swapped into the system as well. So as is the case for the MCT system, you still need to have this light layer cap that does the translation between what you have in the target host component and how you translate that to the framework. But with Neopsy, you also have several other things, which is that you are advertising what you are going to be sending to the component and what you expect to receive from the hub. And one key aspect of the Neopsy CMEPS hub is that it contains a list of fields of everything that could possibly be sent and received by your target model components that couple to it. And what happens is that then the components say, hey, this is all I need to send, this is all I need to receive, and then all of that is automatically set up in these connectors via what Neopsy has as realize phases, so that you pare that down. And so the idea is that every model system has a different set of fields that they specify to the mediator when they create it, saying, hey, for my modeling system, these are all the possible fields that CMEPS will send and receive. And that is the model-specific part of CMEPS that we've created and have abstracted. So what is in the CMEPS name? What does it mean to have a community mediator for Earth prediction systems? Community means that it's a collaboration. Right now, it's a collaboration between NCAR, NOAA, and particularly the Environment Modeling Center at NOAA, which transitions stuff from research to operations. And we're also working with GFDL to make sure that certain aspects of what's needed in CMEPS required by GFDL can be put in there. CMEPS is developed openly on GitHub, and we encourage community code contributions. And since it's an open development, I believe it encourages collaboration as well as innovation. That's the community part. The mediator, as I've mentioned before, is that it is a Neopsy compliant component coupler, and it's designed to flexibly couple component configurations for atmosphere, land, ocean, wave, sea ice, and land ice components using the hub and spoke architecture. And the term Earth prediction systems is that NCAR in particular is moving away from just restricting what we do with Earth system modeling for climate, but also targeting Earth prediction seasonal to and not sub-seasonal, in our case, seasonal functionality, but NOAA is targeting sub-seasonal to seasonal functionality. And so CMEPS is being used not only in their seasonal application for the Unified Forecast System, but also in the hurricane and forecast systems where we're going to be able to, where we are putting in moving nests into CMEPS. So what are the benefits of CMEPS? This is going to be really fast. Okay, so we have Neopsy introduces 4 components, a mediator, a driver, and connectors. The key point is that connectors are automatically generated for you, and as with coupler 7, you actually had to physically construct them into code. Here, they are automatically generated. And that the data run sequence is a runtime sequence. So one of the things about CMEPS is that it does runtime generation of mapping weights. As we're going to different refined grids, this will significantly pare down the ability for the community to introduce new refined grids more easily because all of the mapping will be done online and you don't have to create a plethora of mapping files. So in coupler 7, we had several thousand lines of complex code that had to do with the driver sequence and the mediator sequence. As Rocky mentioned yesterday, for CMEPS, you have a very simple ASCII file that has the run sequence, and the way we're doing it with our workflow is that this is generated automatically. And as he mentioned, components can have different named phases. So as you see here with the syntax, you can have different coupling frequencies. So you have a simple syntax for the driver looping structure. You have connectors with these arrows. These are generated automatically for you. There is no user code. And then the components can have multiple named run phases. One thing I'd like to point out is that if you would like to have a connector between 2 components and not go through the mediator, it's very easy to do that in the run sequence. You simply have an arrow between 2 components. And this is a very powerful idea of how you can mix direct communication between components versus communication with a hub and spoke architecture within an extremely simple ASCII run sequence file. So it really puts us in a totally different area of how we can support different scientific experimentation by the user community. So the benefits of sharing a mediator, when you exercise anything with different use cases, you have a much more robust system. And right now, what we're doing is we're actually sharing the same cap for MOM6 and SCI6 between NOAA and CESM. And the ability to be sharing this has resulted in much more robust caps. So what's the status of CMEPS? All the CSM components are now CMEPS compliant, and as well as the data models, but I'll get to that in a second, and I'll summarize that very quickly. I think NOAA has officially adopted CMEPS for their S2S application, and that's moving into validation and operations. And we're also working with a hurricane application, which will enable regional grids with moving nests to be incorporated into CMEPS. So I want to wrap up. I think I can do this very quickly with the fact that we have a whole new set of data models that we've created that are based on ESFF Neopsy that enable you to swap out the data models for the prognostic components, and they're CMEPS compatible. So as I mentioned before, having data models is extremely powerful because they enable you to turn feedback selectively off and on in the system and also reduce the time spent in debugging and testing. So with these new ESMF-based data models that we're calling the community data models for Earth prediction systems, there's a lot of new functionality that's come in. We had MCT-based data models, but it was, you could theoretically use mapping to do this, but you had to create them on offline mapping files. There was a very simple bilinear mapping that was put in place. With CDEPS, you are leveraging the full regridding capability of the ESMF framework to regrid between your data mesh that comes in and your model mesh. And as a result, you also have multiple regridding options, including conservative regridding that you can easily do just by specifying a runtime setting in an XML file. So the other thing is that as part of CDEPS, we've introduced a ton of modularity with sharecode to be able to ingest these data forcings and map them to your model grid. And we've enabled a different API for the sharecode so that it can be called directly from the prognostic component code base. So now the prognostic component code base actually can do conservative regridding, even 3D conservative regridding of forcing data such as aerosol data, and ingest that into the model and map it to the target grid. So I think I'll skip the next two slides where I've gone into a little bit more detail about CDEPS and just summarize with the fact that I'm happy to discuss all of this in more detail, but I really want to thank the ESMF team for all of the incredibly hard work that they've done and their prioritization of any time. You know, we've really pushed the limit with what they're trying to do in terms of complexity, and they've been tremendously responsive. And I think the framework itself will really take CSM to the next level.